So the second and last speaker of this morning, of today, of the meeting, is Professor Balasubramanian from Chennai, who will talk about Waring's problem.
The cluster, yeah,
Second part.
cluster. Yes.
Fine, please.
Yeah.
How to get good?
Okay. Okay. Very good. Okay. Yeah. Any other question also which you can have, because it's more like making you more familiar with the standard techniques in analytic number theory, and therefore even if and in any case I will not be able to cover the things, I will still be able to see to enable you to read the paper of Shivanic. That's all the aim. Therefore, not giving everything and understanding, explaining all these things. And therefore, if you have specific doubts like that, okay, fine. Okay, yeah, this is a certain sum which comes again and again. For example, in Waring's problem. Therefore, as Professor Drishu was explaining, you start with something like an alpha x power k. And then you want to estimate it. And then you always assume that mod alpha minus a over q less than or equal to 1 over q square. And you will be in the minor arc, and therefore x will not be very small. And also x will not be very, q will not be very big. Okay, they will be in the intermediate range. And then in order to do that, you square it. And then change the variable, then you get an extra new variable and the degree goes down to k minus 1. Then square it, then you get an extra variable and degree goes to k minus 2 and so on and so forth. Okay, those part Professor Deshway has already explained and therefore I am not going to do that. At the end, what happens? When you completely come to the linear form. Therefore, at the end, you get a sum of this form. And the question is, how do you estimate such a sum? Okay? And depending upon, first of all, of course, the x and y, there's a symmetry, and therefore you can choose one of them. Therefore, let me choose the y. Therefore, I want to sum up this funny thing. Okay? And therefore, in particular, let us say you have a sum like that. Y is obviously without mentioning, this is an integer. And let's say even say 0 less than or equal to y less than or equal to y. Y over q, of course, or even alpha. Okay? Yeah, and yeah, how many of you have seen a sum of that type? And how do you say? Yeah, how many of you have seen such type and then how do you sum it up? Or what is the estimate for it? Okay, let's do that. This is, of course, clearly a geometric progression. Always remember E of x is e power 2 pi ix. Since it's e power 2 pi ix, it's a geometric progression, I can sum it up. I can sum it up and then I will get something like that. Okay? This, of course, is somewhat a complicated thing. Okay, it doesn't. But I want to write it as an estimate which is better. There will be no small y, yes. Okay. But in any case, after one step, that will disappear anyway. Okay. Therefore, this is what I have, and I want to estimate it. Okay. And therefore, the estimation is less than or equal to 2 over modulus of 1 minus e alpha. I put this line here for some funny reason. Okay? And this is what I have to estimate. And this, when you look at this 1 minus E alpha, since this is periodic modulo alpha, I can assume that my alpha lies between minus half and plus half. Okay? Which I will assume. And then since again E of minus alpha is a complex conjugate of E alpha, I can as well assume alpha lies between 0 and half. Okay. Therefore, now I can assume alpha lies between 0 and half, and then I take this alpha. Therefore, technically speaking, therefore, this alpha would be really replaced by the distance to the nearest integer. Okay. Alpha I can to the nearest integer essentially because I can translate it by 1. Okay. Therefore, then I can assume positive. Consequently, it will be 1 minus e power minus. Therefore, since it's a little boring to write that, let me write E alpha, but on the other hand, remember this alpha which I am having in mind is really the distance to the nearest integer. Okay? And now I need a lower bound for this funny thing. For 1 minus E alpha. Okay? Which of course, you know, given a complex number, how to find out an absolute value by taking the square root of real part plus the square plus the imaginary part square, etc. But I am not going to do all those things. I am going to do a little simpler thing. I am going to multiply by e power minus alpha by 2, which I am always entitled to do because modulus of e power minus alpha by 2 equal to 1. And therefore, there is no problem in that. And that is therefore is equal to 2 by e of minus alpha by 2 minus e of alpha by 2. And now I can use the theorem of Euler saying that e power ix equal to cos x plus I sin x, which would give you something like 2 over sin pi alpha. Well, that's a 2 over the 2 cancels. Anyway, I am only interested in the upper bound, etc. It doesn't matter, okay? And you all know that if you are looking at your alpha between 0 and half, then absolute value of sin pi alpha is bigger than or equal to constant times alpha. And you also know the constant. Constant happens to be 2 over pi. Okay, but anyway, we are not interested in that. And therefore, consequently, this is less than or equal to 2 over pi divided by alpha. And this alpha being not really the alpha, the nearest integer to the distance between the nearest integer to alpha. It's okay? This probably may not be the best estimate that I can get. In particular, your alpha may be very close to 0. If your alpha is very close to 0, then there is this 1 over normal alpha coming in the denominator, of course, will make the bound to be very bad. Okay? And therefore, I should also have another bound to be used in case my alpha happens to be close to 0. And that bound is given by y or y plus 1. 2? No. 2. Y plus 1. Okay? Therefore, if this alpha happens to be close to 0, then I know how to do it. And if alpha happens to be not close to 0, I can use 2 over some constant over alpha. That constant also I will forget in all my things. I mean, that's unless you are Ramanujan who is interested in the constant, exact constant 7.38, etc., which I am never, and therefore I always forget it. I am a student of Ramchandra, therefore anything up to 10 power 4, etc., do not even exist for us. Okay. And now I come back to this problem. Therefore, at least one sum I know how to do it. Now I have to do both the sums. Okay. Therefore, now let's look at E of alpha xy. This is equal to summation over x. The summation over y I have already done, which is minimum of capital Y and 1 over alpha. Alpha x. Okay? And now this is what I have to sum up. And now let's take a very simple case. Alpha is equal to 3 over 13. In which case, this alpha x is periodic modulo 13. Okay, if x goes by x over 30, x plus 13, it doesn't really matter. Since it's once you have a function which is periodic, you know the standard technique of summing it up. Okay, take up to one period only and see what happens. And if you know what happens in one period, then that is what you will repeat the second period, third period, etc. Is it okay? Therefore, in particular, if alpha is a number like A over Q, then what happens is I can break this into intervals of length Q. Or somewhere I have to put it strictly negative. Minimum of Y 1 over alpha AQ. Alpha, no, X AQ. Okay? And now X when runs over the interval of AQ, then this X A over Q will take the values which is 0, 1 over Q, 2 over Q, 3 over Q, up to Q minus 1 over Q in some order. Okay. It may not be the same order in which A goes. Okay. A will go from 0, 1, 2, 3, or I mean, yeah, X will go from, let's say, AQ plus 1, AQ plus 2, etc. But then this XA over Q will go to 0, 1 over Q, 2 over Q in a different order. But it doesn't matter. This is what I have to invert and sum it up. Okay? And of course, as far as this value is concerned, I am not going to use this. That will become infinity. For that one value, I will take capital Y as the bound. For the rest of the values, I will take this 1 over Q, 2 over Q, etc. Good. And therefore, consequently, that this sum is 1y plus, then there will be a q over 1, q over 2, etc. No, you don't go up to q over q minus 1 because I am not taking the fractional part. I am taking the distance to the nearest integer. Good. Therefore, it will go half the way here and then half the way here. Because the q minus 1 will correspond to 1 over q, q minus 2 will correspond to 2 over q, because if you are taking the distance from the nearest integer, and therefore it won't go q over 1 plus q over 2, but it will go q over 1, q over 2, etc. halfway, and then q over 1, q over 2 halfway. Is it okay? And this, of course, is a harmonic sum. That will give you a q log q. Therefore, this gives you, therefore, less than or is equal to y plus q log q and the number of terms. And the number of terms is essentially x over q plus 1. I have an interval of length x going up to an interval of length x, and I am now breaking it to intervals of length q. And okay? Is it okay up to that? What happens if this is not the case? That's the case which you are looking. Alpha is not A over Q, but alpha is close to A over Q. Alpha minus A over Q is less than 1 over Q square, which I wrote somewhere, which I erased. Alpha minus A over Q is less than 1 over Q square. Therefore, alpha A over Q plus beta with mod beta less than 1 over Q square. This argument does not work, obviously, because I don't even know how they dumb things will. But really speaking, it is not the exact value that I have used. What I have essentially used is that these numbers are 1 over Q apart. Okay? Therefore, they all do not converge near 0. My only problem is if all of them converge near 0. But they are 1 over Q apart. Therefore, there will be one number which is at least 1 over Q. Then there will be one number which is at least 2 over Q. There will be at least one number 1 over 3 over Q because they are 1 over Q apart. And whether I want to know whether I can really satisfy that. If the numbers are 1 over Q apart, then I am already happy. Is it okay? Therefore, I will do that. And in fact, I can use the same argument of breaking into Q. Okay? But to make, since I don't again not bother about the constant and I only want a simpler proof, I will make it to determine the Q by 2. It doesn't matter, I will get an extra constant too, that's all. Then I want to say in this particular range, if I now look at these elements alpha x, when x runs in this range, then the elements of alpha x are distance apart. 1 over 2q distance apart is what I want to say. Okay, once I say that it is 1 over 2q distance apart, then I am happy. Is it okay? Therefore, let's do that. Take an x1 and x2 in this range. And now look at alpha x1 minus alpha x2. And this is equal to, this is at least greater than or equal to alpha into x1 minus x2 by, okay, yeah, minus modulo 1 everything, of course, minus beta into x1 over x2. Alpha is A over Q. Distance, of course. Distance to the integer times minus beta into x1 over x2. Is it okay? I think I want to say that the A over Q part is the one which will dominate. The other part is small. And therefore, I can only look at the A over Q part and then fine. And now look at this funny thing. This number is at least 1 over Q. Because x1 is not equal to x2. And x1 x2 come from an interval of length q over 2. Since they come from an interval of length q over 2, it cannot be 0 mod q. Since it cannot be 0 mod q and they are distinct, therefore A over q into x1 minus x2 is at least 1 over q. Minus beta is at most 1 over q square. And x1 minus x2 is at most q over 2. Because I am looking at the interval q over 2. And therefore, this is bigger than or equal to 1 over 2q. Okay. Therefore, if I now plot these numbers, they are distance apart from 1 over 2q. Good. Consequently, if I plot these numbers, there will be one number here, some B1, and another number here, B2, another number here, B3, B4, etc. Only I go up to half. For the other half, of course, I come from there. Because we are looking at the distance to the nearest integer, and therefore, up to half I go this way, and up to half the way. That is what the distance to the nearest integer is. And now what do I know about this number? This distance is at least 1 over 2q. This distance is at least 1 over 2q, etc. They are distance 1 over 2q apart. Good. And anyway, I don't know much about this number. But this number is at least bigger than 1 over 2q. The second number is at least bigger than 1 over 2q because it has a distance 1 over 2q from the first number, and the first number is positive. I don't know what is the distance, I don't care. And then this number is at least 2 over 2q, and this number is at least 2 or 3 over 2q, and so on. And maximum q by 2 numbers will be there, because the interval itself has length q over 2. Therefore, the first number is at least 1 over 2q, second number, sorry, first number I don't know, second number at least 1 over 2q, third number at least 1 over 2 over 2q, fourth number 3 over 2q, etc. And these are the numbers which I should take and invert. And for the inversion, for the first number, I am not going to use it, because for all I know, the first number can be very small. But therefore, for that number, I am going to use the length y as a bound. And therefore, this number, yeah, is less than or equal to, there will be 1y plus, then there will be a 2q over 1 plus 2q over 2 plus 2q over 3, etc. Okay, and that gives you 2q, y plus 2q log q. Since I am not fighting for the constant, that's okay. And then, of course, take the interval 1 to q, break them into intervals of length x over 2, and so on and so forth. Is it okay? Yeah. Y plus 2q log q, sorry. Is it okay? And in Wales inequality, that's the type of things which you will have. But there are other situations where you will have something more. You will have something more like a minimum of y over x 1 over alpha x. I mean, you may have, the first one, it may not be something independent of x. It may even be something which depends upon x. But that doesn't matter. I can use the same argument. I can use the same argument. I can break it into terms of length q by 2 to q. And then I have essentially like that. And for one of the, okay. For the first one, it will not be y now. It will be y over aq. Therefore, that will be 2 y over aq, I mean, ignoring the constant, so y over aq plus q log q. And then you can sum over a, except for the fact that this sum goes from, a goes from 0 to something. For a bigger than or equal to 1, you can use this idea. And for a be equal to 0, of course, then you have to use something else, depending upon the problem. Okay? Because for y equal to 0, this will not work. A equal to 0, it will not work. For a bigger than 1, you can handle it, and only the small first part, first is 1 to q by 2, that part alone will be there, and that has to be handled separately. Is that okay? Good. Anything else you want? We'll continue then. Okay, first of all, yesterday I did something wrong, and therefore let me correct that. There is an half, which I have forgotten. Okay. And when I was wondering whether it is half or one, Professor this way made a comment, how does it really matter? Okay. And therefore I should explain what the comment, how does it really matter? It doesn't really matter. Okay. Therefore, let me explain why such things do not really matter for us. And when you are doing the estimates, all our estimates are up to some power of x power epsilon. Therefore, we don't care about the x power epsilon. And therefore, if we lose our x power epsilon, it doesn't really matter. Now, let's look at the following, for example. Let A be a given number, fixed number. And this is a simple example. Let me look at 1 over some c power 1/4, c less than or equal to c. I will always use this because this is a notation. And then GCD of c and a over half by c power c and c power half 1/4, c less than or equal to c. I want to say that if you don't mind an epsilon this way, that way, then both the estimates are essentially the same. That's all what I want to say. And even if it were not half, it were 1, anything, the estimates would be the same. Okay, depending upon A is fixed. Okay, let's do that. This, you know, what is the range? What is the value? How many of you know what is the value? C power 3/4. And do you know that's a constant, or is there a constant or no constant? What is the constant? 4/3. 3/4, sorry. 3/4 or power is 3/4. This is 4/3. Okay, in the back bench, how many of you know how to prove such a statement? Would you prove? Sorry. Exactly, that's all. Okay, therefore, this you should know, and therefore, let me give you an exercise. This exercise you should do so that you should be able to do the things. You will need, if f of x is monotonic, summation f of n, a less than or equal to n less than or equal to b, and is essentially the same as summation f of t dt, a to b. The sum is the same as this, up to an error which is O of first term plus last term. Okay, that's an exercise you should be able to do. And once you have that, of course, 1 over c power 4 equal to, the integral of 1 over x power 4 dx, and you know how to compute it. Is it okay? That is it. And now what is this value here? I want to say essentially that is also c power 3/4, maybe as an epsilon this way. That. Okay? Let's do that. Therefore, let's break this sum into two parts. Let us fix in a GCD equal to k, and then this k will divide a, and then you have a k power half, and then you have a summation 1 over c power 1/4, and this c, this k has to divide this c also. Yeah, we'll do that. That's all exactly. Okay. This is much bigger because this K may divide A and K may divide the C, but still the GCD may not be K. I have to only take those A and those C for which the GCD is K. But instead of that, I am taking all, given a K, I am taking all A and all C for which K divides A and K divides C. Whether the GCD of A and C equal to K or not, it doesn't really matter. Okay, but then I will make a comment later, and therefore this can come out, and therefore this little c will go only up to capital C divided by K, because the little c is 0 mod K, and which I am now reading as K times C, and therefore this K comes out and then the C, and therefore this is equal to K times K dividing A, K power 1/4, and then this is capital C by little k power 1/4. Oh, 3/4. And that is equal to summation over K dividing, the C power 3/4 comes out. What you are left with is a summation over K dividing A 1 over K power half. For example, even now, if you replace the 1 over K power half by 1, it is only a divisor function. And therefore, why? This term. That's exactly what I have done later. That will be K power 1/4. Why? Yeah, C is going up to C by K. Okay. Let's do it carefully. You see, what you have, the GCD of AC power K is K power half. That part is okay. And then you have a C. And this K is not running anywhere. This K divides A. And then this K divides C. And then you have a 1 over C power, and this C goes all the way up to capital C. And then you have a 1 over C power 1/4. Is it okay? Yes. And that C I am writing as C dash times K. That's K divides C. Okay? And therefore, this C is C dash times K power 1/4. Then this condition is go over. This C dash goes only up to. This is what I have. I should not have written the same C, but I thought this. Okay. Is it okay? Good. Without going into details, let me say for people who are really bothered about the constants, if you have something like that, you can have a slight improvement over the constant by really writing this is summation over C, 1 over C power 1/4, and then the summation over L dividing A, L dividing C, phi of L. Yeah. Because L dividing A, L dividing C, phi of L is precisely the GCD of L and A and C. And now you can interchange the summation and use the same argument, and then you will gain in the constant unity. That's okay? Good. So far, so good. That's, yes, that is true. You can find out a function f. That's that exactly. I mean, yeah, you can always find out, but then that will become complicated. I tried once with some problem, and I thought I won't be able to do it, and then estimated it. I mean, to find out a function g such that summation GL L dividing n is equal to exactly is equal to the GCD equal to 1, that turns out to be somewhat difficult. Good. Now, with that, now let's go back to our problem. Okay, our problem is that we had this Kloosterman's idea and then wanted to use this Kloosterman's idea somehow to have a specific problem. And the specific problem which we want to have is essentially the number of representation as sum of quadratic form, positive definite quadratic form. Therefore, what is a quadratic form? Quadratic form is something like in let's say two variables. And more variable, it will be homogeneous of degree 2. And when x1 and x2 runs over the real numbers or the integers, if this form takes only positive values, suppose this form takes only positive values, then this is called a positive definite form. And it takes only negative value, of course, it is called a negative definite form. By allowing 0, you can also have a semi-definite form, etc. And we are interested in the positive definite forms. And these positive definite forms is what we want to. Therefore, therefore, the type of questions which we are now going to ask is that whether every n or every sufficiently large n in 4. I should make a few comments at this stage. I am taking exactly 4 variables because higher variables are easy. You can do with standard methods. Only 4 variables is difficult. And if it's a positive definite form, the coefficients will be obviously positive. And the form in which x1, x2, the terms like x1, x2, x5, x3 do not occur, only x1 square, x2 square, x3 square, etc. occur, they are called a diagonal forms. And whatever we are going to say also equally works for the non-diagonal forms also. Okay, and how to do the from the non-diagonal forms is something which you will see first. Okay, we will learn something about the quadratic forms. Okay. First of all, any such quadratic form can be written as this vector multiplied by 4 into 4 matrix multiplied by this vector. Therefore, you have this vector x, which is x1, x2, x3, x4. And therefore, you take the transpose of that and multiply by a matrix and then take the transpose. And any quadratic form will look like that. Is it okay? And exactly how it will look like, let's take a very simple example of 2 variables. Let's take 2 variables and let's see what happens. If you look at that, then the first you have a ax1 plus cx2, and then you have a bx1 plus dx2 times x1, x2, which simplifies to ax1 square plus dx2 square plus, yeah, b plus c x1, x2. Therefore, when you are given the quadratic form, then the matrix seems to be reasonably settled, but not exactly. Because the A is already fixed, that's the coefficient of x1 square. And D is already fixed, it is the coefficient of x2 square. But then only B plus C is fixed. Okay? I don't want that. I want a uniqueness. I want a uniqueness, and therefore I am going to insist from now onwards that this matrix which I am writing is symmetric. And once I insist that the matrix has to be symmetric, then of course B plus C, B equal to C. And therefore, once you know the value of B plus C, then you have that. Is it okay? Therefore, any quadratic form can be written as what is that? X transpose. Okay, I am making a wrong statement. I will correct it in a minute. Can be written like that. Okay? With A as an associated matrix. And developing the theory of the quadratic forms, Siegel realized that it might be a better idea to define like that, which is what we will do. You know that in our discussion, the constant 2 plays a role, but there's a general thing which you will see in the literature. The quadratic form Q is equal to half times X transpose times A times X. Ready? Yeah. I don't want to write the bar, because the bar I have already used in 2 minute situations of the inverse modulo C and then complex conjugate. Yeah. Okay. No, just 2 minutes about what is the quadratic form I will explain, and then we can leave. Okay. Therefore, any such thing looks like that, and with the A as a corresponding matrix. Okay. And I have put a half. This essentially means that if this Q has integral entries, then this A will have the property that if Q has an integral entries, then this A will be the property that AI belongs to 2Z and AIJ belongs to Z. Because of the half that I have written. Okay. And further, you know that every such form can be, symmetric form can be diagonalized. And the diagonal entries would be, of course, the eigenvalues of the form. It's okay? And therefore, this A can be written as P times D times P inverse. For some matrix P and a diagonal matrix D and P inverse. And then after that, you just put X is equal to Py. Then this form, X transpose AX, becomes a form in Y, and that form will be a diagonal form. The corresponding form in Y is diagonal. Which means by just taking the similar matrix, you can always assume it's diagonal. And therefore, I will be even stating the results for a general form, but I will be proving the results only for the diagonal matrix. Because in the case of diagonal matrix, it's easy. Sorry?
Diagonal entry may not be entries of D. They may not be integers.
No, they will be integers because I am putting X equal to Py.
Eigenvalues of A may not.
Oh, eigenvalue, okay. No, it has to be no. I mean, if the original form has integral entries, then one will not have, need not have an integral entries, but there will be a constant n such that when you multiply that NA inverse, that would have an integral entries. Okay, and that N can be, is a constant which can be again computed in terms of A, etc. And therefore, I will forget the problems coming out of that. Okay, we'll continue and we will use this notation. Yeah, first of all, I said that of course it can be similar, it would be similar to a diagonal form, but the diagonal form need not have an integer entries, and there will be an integer n, and definitely the determinant of A already would help, but most of the time it will be much smaller. Therefore, but those questions I will ignore. And then this A of x will denote this x transpose A times x, the quadratic form. Okay, that's a factor of, etc. But anyway, okay. And now I want to prove the following theorem. Again, I'll be proving only for, okay, let Z belongs to the upper of plane and x is R, then E of Z over 2, A of m plus x, summation of course over m in Z power R is equal to determinant A power minus half I over Z power k, which I have not defined yet, and the summation m belongs to 2 power R, E of minus 1 over 2 Z, A inverse of m plus mx. And remember, I am not putting any bar, therefore this m is also an m tuple, R tuple, and x is also an R tuple, and this m dot ax is a standard scalar multiplication. Okay, and A of m I have already defined, A of x, which is x power x transpose A times x, and A inverse m is of course, therefore you take the matrix A and take the A inverse and then do the m, and then this mod A power of 5 pi Z power k into this. This is the theorem which you want to prove. Okay. And this is of course generally true for any A, but as usual I will assume that I am looking at a diagonal form. Sorry? Oh, k is equal to R by 2, yes. This k will come, of course, when you are looking at looking at this as a weight, a modular form, and then when you are want to look at the weight and the level, etc., then this k will come, which is R by 2, that will be weight k. And in fact, I wanted to make it much simpler by looking at that. When Professor Deshwe pointed out, in this particular case, a lot more is known, and therefore you don't need the Kloosterman thing. Therefore, only if you have a coefficient, then you have a problem. Just simple diagonal form, again, various things can be done. Okay. Let's prove that. And in order to prove that, first of all, I need one integral, because, okay, everything, of course, once you go, one advantage of going to the diagonal form is essentially you can reduce the one-dimensional case. You will just split it into one-dimensional case. And in the non-diagonal form, if you write it, then you write the formula and use the transformation of making this A into diagonal and then do the same thing. And therefore, the formal theorem which I want is the following. That's the integral which I am interested in. e power z over 2 y square minus uy equal to I over z power half into e power minus u square by 2s. Okay, this is an integral which is not difficult at all, and therefore I will give you a hand waving proof, and which you would be able to finish. Therefore, let's do that. And therefore, you have an integral over r e power. First of all, the obvious thing is, of course, and you have that. And then obvious thing is, of course, first of all, complete the square. Okay, I have completed the square, and therefore this gives you essentially integral over r e power z over 2 into y minus u over 2 whole square into e power minus u square over 2z. And that is the number which appears here. I am going to forget it. And then, of course, make a change of variable. Is it okay? That's the obvious thing to do. And then again make a change of variable. So that this is integral over r, and then you have a e of z over 2 b square into 2 over z into square root of 2 over z times dv. No, over r. Okay, 2 over z. Yeah, otherwise, of course, I have to prove that the region in which I am moving does not have a pole. That's the only thing, which is, of course, satisfied because I am still in the exponential function. I have no problem. Okay, therefore, the constant I am forgetting because everything will adjust, and then this 1 over root z is already there. And therefore, you have this integral r e power v square. Therefore, if I know how to do this integral e power v square dv, then I am happy. Okay, that's all what we want to do. Okay, therefore, let's do that. Again, because it is v square, I can even take 0 to infinity, e of v square dv. And then we have to do it. And now again, I am going to use, we are in a complex integral, and therefore we are going to, is it okay up to that? Sorry? Directly, meaning what?
2 pi.
E power 2 pi e square. Okay, therefore what you will do is you take an arc and then take this arc, which is the line r e power I pi by 4 goes up to capital R, and then take the arc. When I am taking the circle of radius r, and then I have this real, and then I take the line e power I pi by 4. Is it okay? And then I have this. And therefore, this is the integral which I want. And I would say that this integral gives you nothing. And this integral can be done, explicitly can be done. If I do that, then I am through. Yeah, alternately. Yes. Is it okay? And let me do some hand waving. And if V, in this line, V equal to R e power I theta, and I want to say that it gives you nothing. And therefore, this is integral 0 to, integral from there to that, which is 0 to pi by 4, E of R square e power 2I theta, which is, of course, now it is better, as John says, better to write what you are writing, e power 2 pi I R square, and then e power 2 pi 2I theta d theta. Yeah, R e power I theta, no? Correct. And e power 2I theta d theta. And essentially, now you can estimate this 2I theta, which is the cosine theta, sine theta, and that is around theta. And then integrate and prove that it is nothing, which I leave it to you. And then of course, the first one is E of R square. And then you have I pi by 4 square, which is e power I pi by 2, which is nothing but I. And then the dV will give you e power I pi by 4 dr. And now, as we said, of course, now it becomes a real integral, because E of z equal to e power 2 pi z, it becomes a real integral, you can do that. And that will give you that I power half that you really need. Is it okay? That's the first statement which I need. Now, the second statement which I need is the following. I am going to use Poisson summation, where it is not exactly the way you want. It is a slightly different. And therefore, let me just go through the proof of Poisson summation for a minute to see exactly what I want. Therefore, the Poisson summation normally is treated as like that. That's the Poisson summation, and I am interested in a slight variation of it. In fact, the standard proof of Poisson summation gives you the variation. Therefore, let's see, how do you do the standard Poisson summation? You write like that, and then write the Fourier series for that. And then you prove that this AM is actually the Fourier thing. And then you put x equal to 0. The only thing which I am going to do is I am not going to put x equal to 0. I am going to stop at this stage without putting x equal to 0. Is that clear? I mean, you all see the proof of Poisson summation, which is essentially what it does. Okay? You given this f, you define your capital F to be summation f of l plus x, then prove that it is periodic. Because, okay, and then say that therefore you can write as a Fourier coefficients, and then you compute the Fourier coefficients, and then you get an f hat m, and then E of mx. Okay, if you have an m plus x in this side. And that's exactly what I am going to use. This is the form in which I am going to use the Poisson summation now. Okay, therefore let's recall the theorem, which unfortunately I have erased. This is what I am trying to simplify. This is what I am trying to, is it what I am trying to simplify? Yes, e power z to a m plus h. You see, therefore I need a formula in terms of n plus x, not just n. I'm not having f of n equal to a, I have f of n plus x, and therefore I need a formula. But that will give only extra EMX in the formula, that's all. Poisson, the addition of x will give you an extra EMX, nothing more than that. And now let's do this, and now let's assume that it is diagonal. Evaluated at x plus m. Therefore, in fact, that's what it is. And now you see that clearly splits into the one-dimensional factors. When you write as a diagonal, it splits into the one-dimensional factors. And if you are not diagonal, then of course I will use the fact that it is similar to the diagonal, apply that, and then make it to the diagonal. And therefore, this gives you the one-dimensional factors, and therefore this is e power z over 2, a11, x1 plus m whole square. This is m1 into summation m2, blah, blah. Each one I can do separately and then simplify it. Is it okay? And now I am going to use this Poisson summation. And therefore, the first sum will give you summation over m again, e of mx. That is the only extra thing that would come. And then this f hat m is what I have to compute. Is it okay? Up to that it's clear. I've done nothing new. I mean, just use the Poisson summation. Because it's diagonal, it splits into a one-dimensional factor. And then I have compute the f hat m. And I plan to prove that this f hat m is really an integral of that type. And that's all I need. Okay? Therefore, let's write the f hat m. Let's write the f hat m. Therefore, f hat m equal to integral over r f of y emy, probably minus, depending upon the things, which means essentially you have a summation over r e of z over 2 a11 y1 square, or even x if I want, x1 square. That's all. No, nothing. That's what it is. For this function, I am computing x1 plus m, f of x1 plus m. This is my fx, and this fx is what I am computing, f of x1 plus m. Okay? And that integral is precisely that. And therefore, consequently, you will get to y into, now the a11 will come down, and then the z, because that is the new z, power half, and e of the u is, do I need something more? Any? I don't think there's anything. Okay, wait. Yeah, the determinant of a power of, okay, anyway, what is that I have to prove? This is determinant of a power minus half and I over z power k, which is r by 2, and then you have summation e of minus 1 over 2 z, a minus 1 m plus m dot m into x, and the m into x has already come, and this mod a power minus half has already come, and this I over z power half each time will come, Therefore, it will be I over z power r by 2, which is my I over z power k. And this E of minus u square by 2 is that, and no, what do you say? I mean, that's only x1 square term, there is no x term. One by A. That is the A inverse M. Therefore, I need something like a 1 over 2 Z and 2 M square divided by A11. And where does that come from? Oh, U is M. Where is the U? Oh. Okay. Oh, yeah, this mx is there. Okay, the Fourier transform, there will be an mx. Ah, that's a fine. Okay, that's what I have not written. That's exactly the problem. That is the integral. That e power minus mx I forgot to write, and that's why the problem is. And then this is exactly of that form. And the nu z being z times a11, and the u being exactly equal to m. Therefore, the z equal to z into a11, and now I can use this theorem, and that would give you I over z a11 whole square into e power minus m square divided by 2 times the nu z, and the nu z is z times a11. Okay? Therefore, from that integrated, it follows that this is the pattern. Is it okay? And now, of course, then you multiply all those things. Then this gives you mod a power minus r. This gives us I over z power k, and then you have a summation e power. This is a inverse m, and if a is a11 m square, then it is 1 over a11, and that 1 over a11 comes here, and then 2z comes here, and that's the m dot x comes essentially from our version of the Poisson summation formula. Okay, we are not using the standard version, our version of Poisson summation formula gives you this. Is it okay? Now let me say something else. Okay, let me write that formula. Yes, keep this formula. As it was explained in the, I think the lectures by Ridhaprata Munshi, this Fourier transform essentially helps you if you are summing over residue classes. Then the sum over residue classes in the left-hand side will look odd, and whereas in the right-hand side, the Fourier transformation, that will become better. And that's exactly what our next theorem says, without the m. Therefore, that's a theorem. You take E of z over 2, A of x. This summation over m, A of, yeah, even A. This summation is over m, now congruent to h modulo c. If you want to do that, then when you do the Fourier transforms, it is much easier. Okay? Oh, yeah. That's no x even. I want to see how to do that and why the Fourier transform essentially makes this condition m congruent to h modulo c into a reasonably easier condition which you can handle. Therefore, okay, therefore let's do that. This is what I will be needing. Okay, I will explain why I will be needing that. And okay, therefore now this m can be written as C times m1 plus h. Okay, and therefore this is of course, therefore m1 belongs to z power r, e of z over 2, a of C of m1 plus h. Okay, instead of m, I am writing C times m1 plus h because my m is congruent to h modulo c. Now let us simplify that. This is m1 belonging to z power r, whether you write m1 or m, it doesn't matter. E of z over 2 into a of c into m plus x, where x is equal to h times the c inverse. Earlier I had Cm plus h, and the Cm plus h I am writing at C times m plus x, where x is equal to C times h inverse. And now there is no, the condition on h, the condition that m has to be in a specific residue class only comes here. And now in this generality, we have already done the formula. E of z over 2 into a of x plus m, and therefore I can now substitute. The one advantage is that this, when you have a diagonal form or even non-diagonal form, it doesn't really matter, and you multiply by c, then the c comes out as c square. Okay, for diagonal forms it is easy, but even for non-diagonal form, you are going to take like things like xi, x1, x2, x1, x3, etc. And therefore, when you are multiplying by c, your c square comes out. And consequently, this is equal to m belongs to z power r, e power z over 2, and then you have a c square, and then you have a ci of a plus x. E power z over 2 c square into a of m plus x. This is exactly this particular form which we started with, except that the z has been transferred to z times c square. Okay, and therefore now I can go back here and then simplify what this funny thing means. Because that is equal to this is what I have done. And then I simplify this. This gives you mod a power half minus half as it is, I over z power k as it is. Then you have a summation over m, and then you have e minus 1 over 2c, which becomes 1 over 2c. Ready? Oh, I over z c square, exactly. Everywhere you should get a I over z c square raised to the power k. Yeah. And then this z also becomes a z over c square. And then still you have a hat m plus m into this x is what I know. The x is h into c inverse. Therefore, this is still m dot h divided by c. That's the formula. Okay. Let us keep this formula, and then probably I should explain to you why I am doing all this nonsense. Mod a power minus r, I over z raised to the power a. Then you have a c power r minus r, because that's a c square raised to the power k, that is gives you a c power minus r into summation E of minus 1 by 2 z a inverse of m plus m data by c. There's a c square here and there's a c here. That's the one. Okay. Therefore, I have introduced everything. Okay. And now, let's go back, keep it here. But why am I doing all these calculations? I should explain. Okay, what is these calculations doing? Therefore, now I go back to the Kloosterman. Okay. Now coming to the Kloosterman, one point which I forgot to mention, that you have a estimate for Kloostermans, which is the GCD of m and c power half times square root of c times tc. But on the other hand, there are already other estimates available in the literature if you are taking an average of Kloosterman. Okay. Let me just give one of them without explaining all the notations. Up to epsilons as usual. This gives you something which is mx by c. Oh, whatever I will do. Okay. This is mx by c. Okay, this is the h, yes. It's okay? And therefore, some similar results are known for the average. And therefore, if you are in the situation, then you can actually use the average of this Kloosterman sums and then do much better. 1/6, yes. 1/6 is correct, no? 1/6 is correct, no? 1/6.
1/6, yeah.
Yeah. TMN for 1/6. I'm just cool. Yeah. Okay. Okay, therefore, now let's go back to the Kloosterman, and then we proved various things on the Kloostermans. Let's start with that again. Therefore, I have this generally mu f, and let's recall what is mu f. F is a function which is periodic, and the only condition which I have assumed is f of minus n equal to f of n bar, and therefore it admits a Fourier series expansion. And this mu of f is the constant term in the Fourier series expansion. And therefore, it was written as 0 to 1 f of x e of n, f of x dx. And then we simplified it. And then we got something like a minus 1 over cd to 1 over cd, the summation over c, summation over d in the various ranges. And then you had a real, times the real part. And then you had an f bar, f of x minus d bar divided by c. That's the one which we got. That's the standard one. And we are not going to use that. We are going to use something else. Okay, what is something which we are going to use is 0. Is this correctly written? minus 1 over c to dx. And then we make a simplification. And in one simplification, we wrote various different. Sorry?
Are you okay with 5 minutes?
Yeah. Wait, what happened? Yeah, can I take just a few more minutes? Yeah, this is what we started with. And then, of course, we decided, okay, this was the C and D were in outside. And then we wanted to bring the C and D inside. And once we bring the C and D inside, 2 times the real part of 0 to 1 over CC. And then you have a summation over C, which I had no problem, and the summation over D. And the summation over D was capital C less than or equal to D less than or equal to capital C plus little c. But there was an unnecessarily an extra condition that something is less than 1. C dx is less than or equal to 1. And then you have this f of x minus d bar by c. This is the formula which we are going to use. And this form, therefore, this is what we want to reduce to. Therefore, that is what we want to calculate, f of x minus d bar by c. And what is the f which you are going to take? That's the question. Okay? And then all these things gives you mu f, which is a constant term. Okay? And therefore, now let's do the things. Just, okay, I will stop here. I think I have not even finished whatever I wanted to say. This is my theta z. Let me define my theta z properly. My theta is z. Let me define. Yeah, E of QM Z, you are right, and over M. And this exactly gives you E of Zn or Qn. That is the number of representation. And this is a function which I want to look at. Okay, but this is not really the function which I want to look at. I want to look at the following function. Okay, once I look at this following function, and now if I look at the constant term of this function, then this will be exactly equal to RQN. Since I want to RQN, because see, so far I have done the delta function, which essentially means in some sense, when you write the Fourier series, what is the constant term? I have written the formula for the constant term. And therefore, now I have to write this function so that the constant term will be precisely what I want. Which means essentially this is the function which I want to look at, and therefore this is what I want to do. And therefore, that is the fx I have. Therefore, I should probably make one comment there, which I will stop. And that comment is that we will not be able to integrate it on the real line. We will be able to integrate it only on the higher level. Therefore, we will fix our imaginary part. Okay, appropriately. Say, let us fix our imaginary part, y equal to 17.83. And then your z is equal to x plus I into 17.83. Therefore, that is the set which I am taking. And therefore, whatever I am writing, which looks like a complex number, is really a function of one single real variable. And that is where we will be integrating. And therefore, when you read the book, you may get confused because you will start with an f set and then write that it is equal to g of x. Okay, that we are always doing essentially because we are fixing already a specific imaginary part and then adding it. Okay, and I think I will stop here.